So this video is on Chapter 7, A and B, and it's a little, hopefully it'll be fun because it's a little different than the stuff we've been doing recently. It's on binomial expansions, which involves Pascal's triangle. And first we'll start, well, a binomial, of course, is something with two terms. So this is chapter, let's see, 7, 7A is called binomial expansions. If you hear a lot of background noise, it's because the track team is right outside my door. I've got the door closed, but they're still pretty loud. And if you, so a binomial, you could say A plus B is a binomial. And then if you raise it to a power n, then that whole thing will be the binomial expansion once you work through it and expand it out. And so we could start with A plus B and square it. And then if we did that, we could do that in our head. That'd be a squared plus 2ab plus b squared. And then if we wanted to do a plus b cubed, we could actually use Pascal's triangle to do that. So Pascal's triangle, you're probably already familiar with it. If not, what I'm doing is so the ones are on both sides, and then you just, like, the 2 came from 1 plus 1 gives you 2, and then, so 3 would be 1 plus 2 would give you 3. So the two numbers above, if you add them, you get the number below it. And then you could keep on going here and just keep on going forever and ever. The other thing, too, the first row 1, that's called the 0 row, n equals 0, and this is row 1, row 2, row 3, row 4. And you can see that these rows, I've labeled them with n's because then that matches this n here. So when the n is 2, here's 2, notice the coefficients are 1, 2, 1, and that's 1, 2, 1. So when n is 3, I'm going to use row 3, and the coefficients will be 1, 3, 3, 1. So when I expand, I'm going to space out these coefficients. And then there's a nice little pattern. What happens is you take the first number, a, and you're going to raise it to the n, and then you're going to decrease the powers as you move across. And by the time you get to the last term, there's no longer a power on the a. There's no a at all. I guess you could say it's a to the 0, which is 1. And then once you get back over on this side, you're going to have the b's will be to the n, and then you're going to work backwards. That's how I do it anyway. I go back this way and I make the powers descend, and by the time I get to the first term, there's a b to the 0, so there's no b there. Because these are pluses, these are all going to be pluses. So that's the binomial expansion for that one. Some things to notice, and the book summarizes these, and I will too. So things to notice is how many terms are there? Well, when n is 2, there were 3 terms. When n was 3, there's 4 terms. So there's n plus 1 terms in the expansion. The a's descend as you go down to the right, and the b's increase in power as you move across. And notice, I'm just not even going to bother writing all that down, but you can see that pattern there. Let's see what else. Of course, the coefficients come from Pascal's triangle, so that's another thing. I had some other stuff written down here. Oh yeah, another interesting thing is if you took any given term and you added the powers on the variables, so 2 plus 1 would be 3, 1 plus 2 would be 3, they're always going to add up to n. So the sum of the exponents on the variables is n. Okay, that's pretty much it. So let's move along. Now it's helpful on these if you make yourself a Pascal's triangle so that you can always refer back to it so you don't have to keep drawing it every time. It's not it doesn't take long to draw, so I'm going to have to draw it again because I need it. So 1, 1, 1, 1, 2, 1. You do it enough times and you practically remember them. Plus it's easy enough to add them. Okay, so example 1, we're going to have 2x plus 3 cubed. Okay, first thing I do is I look and I know this is going to be the third row, and that because n is 3, I know it's going to have 4 terms. So it's going to be this one right here. It's going to be 1, 3, 3, 1. So I start by writing those coefficients down. And I give myself lots of space. Kind of come down here. Lots of room to work. And then the first term is going to be 2x to the third. The next one's going to be 2x squared, and then 2x. And there's no 2x here. Now I'm over on the end. I'm going to have 3 cubed, and I'm going to work back to the left. 3 squared, 3, and there's no 3 there. Because there's a plus there, they're all pluses. Actually, you can always make them all pluses. If there's a minus, I'll show you how a good way to handle that. There's a couple ways you can do it. Now, we do need to simplify it. This is 2x quantity cubed, so that's 8x cubed. Here you're going to have 2 squared, which is 4, and then you're going to have 4 times 3 is 12, 12 times 3 is 36. And then the x is squared. Here we've got 9 times 6, so that's 54. And there's just an x, and then 3 cubed is 27. So that's simplified, beautiful, wonderful example number 1. Now I have to go to my new page, and my Pascal's triangle is gone again. But the next example is going to be with a negative, and it's still going to be n equals 3, so that's 1, 3, 3, 1, give myself lots of room. And then the a is x, so x to the third, we don't need the parentheses, so x squared, x, there's no x here. And then negative, what you can do is think about this as plus a negative 5. So I have negative 5 in parentheses to the third, and then I'm going to descend as I work back to the left. My negative 5 is in parentheses. There's no negative 5 on that one. And then put pluses in between. So we've got x cubed. Negative 5 squared is 25 times 3 is 75. 25 times 3, 75x squared. Oh, something is wrong. That should not be a 2. I've got a 2 there. So this is incorrect. Let's fix that. Sorry about that. But I caught myself because it didn't look right. So that needs to be fixed too. Oops, that's not an erase. Okay, we'll fix that. Okay, so that would be negative 5 times 3 is negative 15. X squared. Here I have 25 times 3 is 75. And then negative 5 cubed is negative 125 times 1. The other way you can do this, although I think the way that I did it is really a good way to go. I'm going to recommend doing it that way. I think you'll be less likely to make mistakes. But you can notice the pattern when the second number here is negative. The pattern is plus, minus, plus, minus. Example 2. Expand, x minus 2 over x to the fifth. This is not a polynomial, because polynomials, you can't have a variable down in the denominator like that. But we could still expand it. So this is Pascal, so it's to the fifth. I'm going to just take a little shortcut here and start off with my Pascal's triangle right there. And then that'll be 5, 10, 10, 5, 1. So n is 5. That means I have 6 terms. So this row right here. And I've got lots of space, so let's spread those babies out. So we have lots of room to write. 1, 5, 10, 10, 5, 1. And then x is my first number here. So to the fifth, to the fourth, to the third, squared, x, and nothing. Now over here, let's change this to plus and negative. I'm going to have negative 2 over x to the fifth, then negative 2 over x to the fourth, working backwards, third, squared, to the 1, and then there's none there. And then we can put plus signs in between. And now it's just a matter of simplifying. First one's easy. That's x to the fifth, of course. Then here I'm going to have negative 10. And this is x to the fourth over x, so that's x cubed. Here I'm going to have negative 2 squared is 4. 4 times 10 is positive 40. I'm going to have x cubed over x squared, so that's x. Here I'm going to have negative 2 to the third, that's negative 8, times 10 is negative 80. X squared over x cubed, so that means I'm going to have an x down on the bottom. Then here I'm going to have negative 2 to the fourth, which is positive 16. 16 times 5, sorry, I don't know that one. Okay, that's 80. That's positive 80. And that's it's x over x to the fourth. So that's x cubed on bottom. And this last one is negative 2 to the fifth. That's negative 32 over x to the fifth. And I'm noticing too, I'm seeing a pattern here, and that's nice. So that's kind of cool. And we also see the signs alternating all the way through. That's kind of fun, isn't it? I enjoyed that one. And would you believe it? That's 7a in its entirety. We are ready to do 7b, which is, I just love 7b. Oh my gosh, I don't know why. I've always liked doing these. Binomial coefficients. I hope you do too. Now this is going to involve factorials. N factorial, that's written like so. N factorial means you take n and you multiply it by each successive integer all the way down to 1. So for instance, if you had 5 factorial, that'd be 5 times 4 times 3 times 2 times 1. N factorial can be written as n, because 5 was the n, this is the first one, and then the next number is n minus 1, and then the next number is n minus 2, and so on, all the way on down, and then you can just say on down to 3 times 2 times 1. Also, so this is handy to know, by the way. I would recommend writing that down. It's good to know that. Also, oh, by the way, the n has to be greater than 1 or equal to 1 for that. Oh, never mind. That's something else. No, that's true. Oh, yeah, you can leave that. Never mind. Also, you can write n factorial is the same as n times. Now, all of this could be thought of as n minus, here, that's not a division bar, that's like a little bracket. This is the same as n minus 1 factorial, right? So n factorial is the same as n times n minus 1 factorial. That's really important. Super important to write that down. Also, that is very helpful in understanding what 0 factorial equals. What is 0 factorial? Well, let's do 1 factorial to help us answer this question. 1 factorial, if I use the formula right up here, would be 1 times n minus 1. That would be 1 minus 1, which is 0 factorial. And 1 factorial by this example up here is just 1. So I know 1 factorial is 1, and that means 1 times blank would equal 1. That means 0 factorial has to equal 1 in order for 1 factorial to equal 1. So 0 factorial is equal to 1. 1 factorial is also equal to 1. So keep these in mind as well. First example, well, it's example 3, the way the IB book does it, is to evaluate 4 factorial. That's pretty easy. It's just 4 times 3 times 2 times 1. 12 times 2 is 24. Letter B is more interesting. 5 factorial over 3 factorial. We're going to do this by hand. No calculators are needed. Because if I do 5 factorial, that's 5 times 4. I'll do it the long way first. 3 times 2 times 1, all over 3 factorial, which is 3 times 2 times 1. Well, notice that the 3 factorial cancels out with this part up here. So you can think of 5 factorial as 5 times 4 times 3 factorial, all over the 3 factorial down there. And then those will cancel out, and you just get 5 times 4, which is 20. That's why you can do these division, these quotient ones so fast often, is because you can do so much canceling. And if you're good at doing stuff in your head, it's really fast. As long as you don't have super, super big numbers to work with. I remember doing these in high school and liking them back then too. I always just thought they were so much fun. So you could try this one on your own, and then I'll do it too, of course. So I've got 7 factorial, that's 7 times 6 times 5 times 4 factorial. But I've got a 4 factorial on the bottom. So this 4 factorial here is going to cancel with this 4 factorial down here. And I still have a 3 factorial, which is the same as 3 times 2. I don't even write the 4 factorial over 4 factorial. I just do that in my head and think, okay, that's going to cancel out. But I just showed it there so you can see what's happening. And then I notice 3 times 2 is 6, so that's cancels. I've got 7 times 5 is 35. Boom, done. I mean, these are just so fast. It's actually faster to do these by hand than it is to type them in the calculator, often. Especially with these smaller numbers. Well, that's all the ones I have for those. Now we're going to do something called n choose r. So n choose r is written like this. Well, that's one way to write it. Another way to write it is n choose r. It's also the combination, so I'll write here. N choose r is a good way to say it. You can also say the combination of n things taken r at a time. Like, for instance, say you had 7 people in the room and you wanted to choose a committee of 3 people. Let's choose a committee of 3. So you would say 7 choose 3. You would write it like that, or you could write 7 choose 3. And when you're choosing committees, 3 people, does the order matter? If I choose Jason, Sarah, and Tamara, it doesn't. That's the same committee as Sarah, Jason, Tamara, right? The order that I list the names doesn't make it a different committee. It's still the same 3 people. So that's just something to keep in mind. That's when you start studying combinatorics and counting how many ways there are to do things. You use this n choose r all the time. Well, you also happen to use it in binomial expansions, which is so cool. That's what's so neat about math, is how it relates, just all fits together so neat. And it's also related to Pascal's triangle. N choose r, there is a nice formula for that. So I'll give you a couple of different notations. The IB book has another weird way of writing it that I'm not used to. You can look in there. I can't remember. It was really funny. Like the n was kind of in a weird place. This is the same as n factorial over r factorial n minus r factorial. Now you will have that formula on your IB formula sheet, so you won't have to memorize it. For doing all this homework, though, it's handy if you have it memorized. It's just faster. So let's do an example. We're going to evaluate these by hand. And then I will show you how to do it on a calculator, because some of them with the bigger numbers that would be a lot of, it'd be faster just to type it in your calculator. But these ones that we can do in our head, by all means, we will do by hand. So this means 5 choose 2. So I'm going to do 5 factorial over 2 factorial and then 3 factorial. Because these two numbers are going to add up to 5. So it's really fast to just, you can see it pretty quickly. Because this is r is 2, and then this is 5 minus 2, which is 3. Okay, well anyway, let's do it. So you've got 5 times 4 times 3 factorial, but 3 factorial is down here, so those are going to cancel, so I'm not even going to write them. And I've got 2 factorial, which is just 2 times 1, or 2, and I've got 20 divided by 2 is 10. If you know what you're doing, you can do this faster than I can explain it. Letter B, try this one on your own. 11 choose 7, and then I will do it. So we've got 11 factorial over 7 factorial, 4 factorial. Because automatically I'm just doing, 11 minus 7 is going to go right here. And then I'm going to do 11 times 10 times 9 times 8 times 7 factorial, which is going to cancel with this 7 factorial. So I'm not even going to bother writing it. And then I've got 4 factorial on bottom, which is 4 times 3 times 2 times 1. And 4 times 2 is 8, so those will cancel. 3 goes into 9 3 times. I've got 30 times 11. Is that a good way to do that? I'm trying to think of the fastest way to do it. Anyway, yeah, let's do, because it's 10 times 3 times 11. Or 33, you could do 11 times 3. 33 times 10, let's do it that way. Then it's 330 and it's fast. We do it in our head. Great. How about this one? Example 5. Letter A, 6 choose 6. Okay, that's going to be 6 factorial over 6 factorial, and then 6 minus 6 is 0 factorial. 0 factorial is 1, so that means these are going to cancel out to 1. What about 6, or how about 7 choose 0? 7 factorial over 0 factorial. 7 minus 0 is 7 factorial, and that's also going to be 1. And this should make sense, because if you had 6 people and you were choosing a committee of 6, how many ways are there to do that? There's only one way to do it. Or if you have 7 horses and you're choosing a 0 of them, well, there's only one way to choose 0. So hopefully it makes sense. And sadly, that's all I have. So we have to stop.